So let's start by, we have the same problem as everybody. Okay, it's really slow. Let's start by looking at the type of experiment physics you would like to understand. Most of you have probably seen this kind of introduction many times, but I will give a few more details than usual, and I think there should be for most of you some new aspects. So what are quantum Hall experiments about? So one looks at a quasi two-dimensional system of electrons. This is, so to say, this blue layer here, that are subject to a perpendicular, very strong magnetic field, the yellow arrow. And one forces a current through such a quantum Hall sample, that's this I here, and measures the transversal voltage. So I call this the Hall current and the Hall voltage transversal to each other. And one does this usually at very low temperature. So to produce such a two-dimensional electron gas, one has such a heterostructure of different layers of semiconductors. And in a neighboring layer, usually one puts some dopes by some atoms that have an additional electron. So actually, and the layers are such that the electrons go into this blue layer, the excess electrons from the doping, and basically the positive charges in the neighboring layer, they produce something like a confining potential also for these electrons in this layer. Okay, that will be not too important, but somewhat important, as you will see. And what you measure in the experiment is the Hall resistance, so to say, the quotient of the Hall voltage and the Hall current, or the reciprocal value, which is then called the Hall conductance. Okay, and the first thing I would like to emphasize, because this is also taken for granted, one has to be very patient, is that when you make this experiment and compute the resistance or conductance in this way, what you really assume implicitly is Ohm's law for Hall current. Because what you assume is that this quotient here is constant independently of the size of u or I you put there. So you assume a linear relation between the two. Okay. Okay. Not too much. So this is how such a typical Hall sample looks like. So this would be the two-dimensional, quasi-two-dimensional heterostructure. So in such an experiment, these quantum Hall bars can have a size up to 1 centimeter. So they are definitely not microscopic objects, but mesoscopic or even macroscopic. The Hall voltages you measure can go up to 5 volts. Again, it's not an extremely small voltage. And the Hall currents go up to 200 microampere. So also these are not extremely small currents. And a quantity that will be, so to say, central in all what we will be discussing is the gap of the system, the spectral gap of the corresponding system. And the typical gap will be of size 10 to maybe 100 milli-electron volts. So the typical gap will be much smaller than the voltages you apply on that. Okay. And what you then find, and this is the surprising finding, is depicted in this graph, is that if you plot here, and this is this staircase function here, the Hall resistance, the Hall resistance as a function of the applied magnetic field, what you see is not a linear relation, what you would expect from a classical description, from the classical Hall effect, but you see that you have these pronounced plateaus in the Hall resistance. And it turns out, and that was the big discovery, that the values of these plateaus, if you would plot the inverse, the Hall conductance, then these plateaus would be at integer multiples of a fundamental physical constant, the consisting constant, or the inverse of the consisting constant. I'll show you what it is in a second. It's basically E squared over H. Okay? And you find that these plateaus appear for different materials, for different experiments, for different sample sizes, for different temperatures, for different purity of your sample, always at exactly the same value. So this is the kind of universality Jerry was referring to in his talk. Okay. And one other thing you see in this picture, which will not be so important for us, but just to explain the picture completely, is that if you measure the conductance or resistance in the direction of the current, so if you measure the voltage drop in the direction of the current, you find that within the plateaus, it's zero. There's no voltage drop along the current. So, but only if you go here from one plateau to the other, you find resistance in the direction of the current that is non-vanishing. Here, I mean, what you do actually in the experiment, you force a current along the bar. I mean, here at these things, you can connect whatever your devices are. And what you do is you force, I mean, it's easy. You force a current through here because it's, I will say something about this. These experiments are extremely precise. So you find in good experiments, you find that these plateaus are at the expected integer values. I think here, I put it here. So the whole conductivity or conductance is the distance of the whole conductance to an integer multiple of this constant. The relative accuracy is 10 to the minus 10, so 10 digits, close to the alpha measurement you show. So actually, it's so precise that the quantum Hall experiments are now used as the standard for resistance measurement. Yes? This is what we will be discussing. I mean, we will come to this. So I just want to give you the physics, and then we come to the mathematical description. Okay. So these are extremely precise measurements. And to get to this precision, what you really have to do is you have to force the current and measure the voltage. You could do it the other way. You could apply a voltage and measure the current, but it seems to be easier to stabilize the current than to stabilize the voltage experimentally, so that's what you do. I say this because in the models we will be looking at, we will put the voltage and compute the current. So we do it the other way around. But we come. Okay, so what we want to explain from first principles is many things. First of all, can we explain why we have Ohm's law for Hall currents? Of course, proving Ohm's law in general is a very difficult open problem. We will see in this case we can do it. And then explain why we get this universal value and why they are so extremely robust against any type of perturbation. So this is this universality. Whatever we do, I mean, if they're impurities or not, doesn't matter. If you change the temperature a little bit, it doesn't matter. The size of the sample doesn't matter. It doesn't really matter if the species is perfectly homogeneous or not. All these things don't matter, and they don't matter on this level. So this is what we would like to explain in the starting from our basic model. Okay, so now I give you some further background you need to understand in order to appreciate the mathematical models we will be looking at. And this is more or less the standard explanation you find in physics textbook of this phenomenon that probably you have all seen. So if we assume that our electrons are non-interacting, and we look, and then we look at a very simple model for a particle in magnetic field, the so-called Landau Hamiltonian, which is just the magnetic Laplacian on the plane. If you compute the spectrum of this, so it's a single particle in an infinitely extended plane with a perpendicular magnetic field, you find at zero field, this is just the spectrum of the Laplacian, the positive half line. But if you have a non-vanishing B field, you get discrete eigenvalues, equidistant, and the size of these eigenvalues and the gaps between them goes linear and E. These are the so-called Landau levels. These are eigenvalues, but they are, of course, an infinite degeneracy. Okay, this is maybe not the perfect model to do this. So a slightly better model would be to say, okay, we have to look at electrons in a crystalline background. So let's put some periodic potential and the magnetic Laplacian. What you find at zero B fields are typically these so-called Bloch bands. So the spectrum is not one interval, but a union of intervals, possibly with gaps in between. And then if you turn on the magnetic field, what you expect is that again, Landau levels at the band edges, like down here, develop. If you increase the magnetic field further, many things can happen. And I will show you in a second what can happen. I should resist the temptation to use this. Okay. So, and what is actually assumed in this experiment is that the material in the middle layer, in the blue layer, is a semiconductor. So that means that the chemical potential lies in a band gap. That means that the lowest band or the lowest bands are completely filled with electrons. So remember, we have the non-interacting picture, and that the next band is not is empty. However, then we add the doping in the lower layer, so we get excess electrons which go into this system, and they fill up part of the next Bloch band. That's the idea. Okay. Oh, sorry. They fill up part of the next Bloch band, and then we apply a magnetic field. So we are in this situation where we have one Bloch band and these Landau levels within the Bloch band. And the idea is that the plateaus in the conductance appear when here integer number of finite number of Bloch bands is completely filled and all the others are empty. Okay, so if this effective chemical potential with the doping lies in the gap of this Landau type Hamiltonian. And actually the relevant subspace, the relevant physics happens within such a Bloch band with partial filling and the corresponding Landau level. So that's a picture to have in mind. And to see what this sketch here really looks like, if you make a model Hamiltonian for it, for one Bloch band plus a magnetic field. This is the so-called Hochstadter Hamiltonian. This is just the discrete magnetic Laplacian. Then you see here at zero field, the spectrum is just an interval. And if you turn on the magnetic field, I didn't put it here, the axis, then you see these Landau levels emerging. But for larger B fields, you get this nice, beautiful, but relatively complicated spectral structure. Okay. And the idea is we see quantum Hall plateaus when our chemical potential is in a gap, means here in a wide region of this butterfly. This is called the Hochstadter butterfly. And I give you a different picture of the same butterfly, where here the idea is that the black parts are the spectrum of the operator, and still one body Hamiltonian. But here we colored the white part, the gap, or not we, but this is due to the other on this picture. We covered, so to say, the parts that are not in the spectrum by color. So these are really the one color here is one connected component in this plane, open set connected component of this resolvent set, and it's colored actually by the corresponding Hall conductance. If in this non-interacting model, you would put the chemical potential here, anywhere, so you would have a point anywhere here, B field, and a chemical potential lying in the blue region, your Hall conductance would be exactly -1. And in the red region, it would be +1, -2, +2, and so on. Okay, slowly. Okay, so of course, you have a finite resolution here. You will not be able to zoom in. So, okay. There has been a lot of work on these kind of operators. So actually, I mean, this will not be important to, okay. So what you see, for example, here is that at certain values, you have, let's say here, this is the value 1/3 in natural units. So you have 1/3 flux per unit cell of the lattice. You see 3 intervals of spectrum, these 3 intervals here, that you can easily prove. That if you have 1/3, you have 3 intervals. And if you have flux P over Q, you have Q intervals. And the big question, mathematical question, what happens at irrational magnetic fields, and to prove that you have an infinite number of gaps open. This gave Avila a Fields medal, but will not be important for us, because you can imagine it's impossible to even have I mean, it's very difficult to have nearly homogeneous magnetic fields in an experiment, and certainly it would be completely impossible to design an irrational or rational magnetic field in an experiment. So the mathematical results are really beautiful, but completely irrelevant to understanding the problem. Okay, but back to the explanation of this plateau. So the idea is now, the very naive idea would be now, okay, we have here, due to our doping, a fixed chemical potential. Our system is neutral, so we cannot change the density of particles in there. So if we turn on the magnetic field, we should go cut through this picture like this here. And if we go through different colors, and these are the plateaus. This is not completely wrong. This is the idea behind it, that filling these magnetic Landau levels here will lead to integer conductivity. However, the picture is not completely correct, because if we would really do this in this ideal model, we could not design an experiment where we go like this through the picture, because if we change the magnetic field, the density of states in the Landau level changes, but our density does not. So the moment we have a filled Landau level and increase the magnetic field, the Landau level would immediately contain more electrons and would not be filled anymore. So we would not see the plateaus. We would jump from one end of the plateau directly to the other, because changing the magnetic field would immediately deplete one Landau level or populate another one. So the common law is that you see the plateaus because of impurities that lead to Anderson localized states that can be filled when changing the magnetic field. But this, I claim, is not the correct view on this. I did actually spend some time on trying to figure out what physicists say about this problem. And I think I will now explain you why this is probably not the right picture to explain the plateau. Why? Because in our hall bar, and I will be done with the physics soon, don't worry, there will be math, more than enough. In our realistic hall bar, we cannot ignore the interaction of the electrons. In particular, we cannot ignore the Coulomb interaction. What happens if you have an electron gas? What do electrons do? They screen external fields if they are mobile. So actually, you cannot neglect screening effects in these hall experiments. So let me show you first a very nice picture which I found in a math paper of Elliot Lees, Jan Phillips, here. Hi, and Jakob Ingvarsson, where they looked at screening and electron density in strong magnetic fields. That's exactly what we have here. They looked actually at confining potentials, I think, that are more or less harmonic potentials. So they called this quantum dots. So you confine the electron gas in a harmonic potential. And then they compute the density of electrons that develop, because what do the electrons do? You have this external potential, they screen the gradient. As soon as an electron sees a potential gradient, it will follow it, it will move until the electrons, if they are mobile, screen the complete external potential. And what you find is that at zero temperature, you get a profile like this. But if you turn on the magnetic field, you get steps like this. Let's look here at this large magnetic field. So you get the part where you have a varying density, but then you have a plateau in the density. That's not the density in space. Why do you see this? Because of the Landau level. Suddenly, basically the kinetic energy spectrum changes. Suddenly only a discrete levels of kinetic energies are reachable. So what you see is development of the plateau. And these are regions in space where you really have an integer filling of your Landau level without impurity. And in this paper, they actually prove, I mean, this is computed from the corresponding Thomas Fermi or magnetic Thomas Fermi approximation. And in this picture, they prove that in a certain limit of many electrons, Thomas Fermi is a very good approximation to the truth thing. So this is what you expect also in these hall bars. The only difference is there due to the external, due to the doping and the boundaries. Here we have an effective potential that confines only in this direction. Of course, also in this direction, but we usually think we will make the assumption that, or people make the assumption when they model these experiments, that in this direction it's very much extended. So we think that it's translational invariant in this direction and have a confining potential in the transversal direction. So, and of course, physicists know this, and when they really want to get extremely good theoretical models of hall bars, they take this into account. They can even measure where the hole currents flow in these hall bars. So this is now a complicated picture. I will not go through all the details by Rolf Gerhardt. Actually, this started in the early 90s, and this is the review article if you're interested in, where he also gives a lot of references to experiments. He's a theorist in the group of von Klitzing. And just to emphasize what you see here, the different colors are temperatures. So let's look at the lowest temperature. Here, that's this light blue thing. And I'm sorry that it's not so visible, but I hope you get the idea. And actually, this looks so complicated because he wanted to, this was a picture where they tried to modulate the doping and see what the effect on these plateaus is by modulating the doping. So what you see here is the density. Okay, that's the light blue curve. And you see here these plateaus. These are regions in space where you have integer filling of your Landau level. Okay. And this is now transversal cut. So if you think about the whole thing, then this will be strips in the whole bar, which are called incompressible strips. Here you have integer filling, and now if you apply a voltage here, so this is the total voltage drop along the across the bar, you see that in these regions where the density varies, the voltage drop is the local chemical potential is constant because of screening. You don't see a field, nothing happens, and only within these incompressible strips you will have a voltage drop, and so on. So what you see is that the whole, and then what they do to explain the whole current is they say within these strips, we just apply the conductivity model for integer filling of Landau level. Okay. Good. And now if you vary B, actually what you will see that just the arrangement here changes, and the width and the location of the strip continuously changes from one end of the plateau to the other, but you don't need any Anderson localization or whatever to explain that if you vary B, that the strips remain there and lead to an integer quantization of the function. Okay. Having said this, what type of question are we now trying to address mathematically? Basically, what we are going to show is, or try to show, is that the conductivity model in these regions here, where you have a more or less linear potential, so constant electric field, and integer filling of Landau levels, that in these regions you get the conductivity model that actually in these papers is just assumed without further consideration, that you have Ohm's law and the quantized conductor. Okay. Good. Now it took half an hour for this, much more than I wanted. Now let's look at the mathematical models we will address. So first of all, we will not look, maybe I leave it like this. We will not look at fermions or electrons with Coulomb interaction. We will not model the screening. Okay, we will just believe that there are these incompressible strips, and we want to describe the physics within these strips. So we will consider fermions with short range interactions only, because the other problem is just too difficult. Okay. We also work in the tight binding approximation. Yeah, we mentioned this already. That means we will look at models where the configuration space of the electrons is really a lattice, so the position space. This is standard, and that just means we forget about very high energy. Since we're looking at the physics near temperature zero, that is not a problem. And we will look at infinitely extended systems, where the only assumption we will make is that the system, before we apply the whole voltage or the current, is in a gas ground state. So actually we make a model where we are at temperature zero, and the modeling assumption is the gap in the ground state. I will explain this in detail. And we think of this now really as a model for the physics within an incompressible strip in a quantum hole bar. Why do we want to look at infinitely extended systems? The reason is one reason is we can ignore the effects of boundaries without putting the system on a torus. So actually, when you look at the math on these kind of problems, the math literature, they are mostly people look at systems on a torus. Why? Because if you have a system on a torus, you have a finite number of electrons. You can describe everything in the usual Hilbert space. Quantum mechanics formalism. As we will see, if we look at infinitely extended systems with infinitely many electrons, we have to slightly change this mathematical formalism. And But why do we also not want to have boundaries? We could have just cut off and include the boundaries. Because these type of systems, you heard about this, topological insulators, I will speak about this also in more detail. Once you introduce boundaries, your spectral gap closes. So basically this modeling assumption is incompatible with boundaries in these type of systems. So that's why people like to put it on a torus, no boundaries. But then this has the disadvantage that when we take it seriously, that in these experiments, the gaps come from external magnetic fields, then on such models, the magnetic field is not a continuous variable, but it's quantized. And you will see that for some questions, at least, this is important. And the other thing is that we can model this linear potential drop on a torus. It doesn't work. I mean, on a torus, there is no constant electric field that you can model by a linear potential. So these are some advantages. Then another thing is, of course, as you all know, that some properties that are approximate in finite systems become exact in the thermodynamic limit. In infinite systems, in particular, we want to describe or we want to characterize and define phases and phase transitions. So so-called gap phases of matter and phase transitions between them. And this is easier or more clearer, I would say, in the infinite volume. And last but not least, the modeling assumption of the spectral gap in the infinite volume is very clear, and we will be able to really, as you will see, this will be the only modeling assumption apart from short-range interactions that we have to make. So we will have extremely general statements about this universality, while if I go to finite volume and torus geometries, and then take a thermodynamic limit, I have to make assumptions about properties of finite volume approximations, which are typically not available or extremely hard to prove. Okay, so this is some reasons for the type of why we look at certain type of models. And now, before I start with the math details, just a short course overview. So today, physics background, a bit about the models, and I would like to tell you what kind of questions we ask and answer in this course. And then tomorrow, I will basically take some time to introduce some mathematical tools, which we need for this type of problem, but which actually have been used in the recent, developed and used in recent years for many other questions in quantum statistical physics. And then I will, 3 and 4 are the main results. One is the question, how do we define conductance properly in such kind of models in such a precise way that we can later derive things like Ohm's law and quantization. And then in part 4, I will talk about a proof of Ohm's law in these kind of models. And in the last part, I will talk about gap phases and why and under which conditions we can see integer quantization and other things. So, but my idea is interrupt me if I'm too slow. I can always cut in the last part. I mean, if you have questions, interrupt me. I'll take the time to answer. Good. So now we come to the modeling. So as I said, we look at systems in infinite space. So our position space is ZD. For the moment, I look at D dimensions, but later on the dimension will be 2. But many things can be formulated and done in arbitrary dimensions. So we look at fermions on a lattice. So recall, I mentioned this already. So the n-body Hilbert space for fermions on this position space with some spin or internal lattice degrees of freedom Dn is the n-fold antisymmetric tensor product of the one-body space, and then the corresponding Fock space is defined as the direct sum of all these Hn. And so if you have not seen this, this looks strange, but this just means that an element, a vector here is just a sequence of vectors where the psi j lies in the j-body Hilbert space. And the natural norm or inner product on this. Sorry, the little n could be spin, but could be also other degrees of freedom of a lattice. For example, if we want to go to an hexagonal lattice instead of ZD, we would have to combine 2 points in the hexagonal lattice into one side here. And then the hoppings between these 2 points within one, I mean, this is the Bravais lattice, and there could be a more complicated lattice, and this would be just a sub-lattice of the real one. You could have complicated atoms within the lattice, with model several Bloch bands. So this n can mean many things. It's just important that it's finite. Okay. So this is the Fock space, but the problem is if you look at the vector in Fock space, it will be a direct sum. It will be basically, if you like, a superposition of states with finitely many electrons. There will be no state in Fock space that describes our infinitely many electrons with constant density. So what you do is you go to a slightly different picture. So what we define now are the observable algebras AM. So M is the subset of ZD. Then we denote the bounded operators in Fock space that are generated by the annihilation operators and creation operators for points within the set M by AM. Okay? Where I think I don't have to explain it, and if I have to explain it, I will not do it properly. So I assume that you know this, of course, that these creation annihilation operators, the fermionic ones, satisfy these canonical anti-commutation relations. And since we're on a lattice, I mean, these are perfectly well-defined bounded operators. Okay. Good. So remember, AM is the algebra created by the creation, generated by the creation and annihilation operators on points in the set M. And we define the so-called algebra of local observables as the set of all operators, bounded operators in Fock space that lie in some AM, for some M that is finite, a finite set. So these are all local operators, are those which have finite or complex support. And the so-called quasi-local algebra, the K algebra, is the corresponding algebra you get if you allow that is generated by all annihilation and creation operators on the lattice. And if you have not seen this, an important thing is that this algebra is strictly smaller than the bounded operators in Fock space. And that means, in a sense, that why did I do this? Okay. One step after the other. So, so this is the so-called quasi-local algebra. And we need to introduce some subalgebras. We will see why this is very simple. There is an automorphism of this algebra that where you just multiply each creation operator with an e to the I5, so you attach a face to the creation operator, and then you extend this map just to a linear map on the algebra by the usual rules. So you get this on the joint operators, you get the negative face and so on. And one defines now the even quasi-local operators as those that don't change if I apply a sign change to my creation annihilation operator. So basically it means I flip every creation annihilation operator gets a minus. So these are called the even operators. These are just the sums of monomials that contain an even number of creation annihilation operators. And the set of gauge invariant quasi-local operators is the set where of operators that don't change at all under this automorphism for any phase phi. And this is just a different way of saying that I have the same number of creation and annihilation operators in each monomial, so that the phases cancel, which just means that they commute with the number operator. But in this setting, it's not so easy to say what it means, so we formulate it in this way. So AN are those operators that don't create or annihilate particles, and A plus are the even ones. Pardon me? Yeah, I mean, we have to. I mean, for local operators, I would have the number operator on a domain that is strictly larger. Then for the on the quasi-local operator, I could also formulate it this way. But this is the way people like it, and so they call it gauge invariant, and so I introduced it. But you're right. Since we are, I mean, I'm always thinking about the spin system. Since we have this Fock space structure, we could just say these are those that commute with the unbounded number operator on Fock space. Okay. Good. So what is special about these even operators is that if you have disjoint regions in space, M1 and M2, and one operator supported in M1 and one operator supported in M2, if one of them is even, then they commute. Okay, usually we have these anti-commutation relations, but if one is even, it commutes with everybody else that has disjoint support. And you will see that somehow this locality structure will be extremely important for everything we will be doing. That we can somehow look at this infinitely extended system locally. And this basically is the key ingredient for that. Okay, so the Heisenberg evolution, time evolution on this observable algebra is now generated by on this algebraic setting, what is called a densely defined derivation, which I write as LH and often call the Liouvillean. So this is basically the Heisenberg equation on this algebraic level, where usually in the Heisenberg equation you have here the commutator of H with A, which I replaced by this LH. But actually LHX on a operator A exactly, or I mean these derivations we look at will be, or I will also call Hamiltonian. They are sum of local terms. So for each point in the lattice, we will have a local Hamiltonian Hx, and the action of this is just commuting with all these local guys. And under certain conditions, we will work out. This really defines, again, a local observable. You think if this A is sufficiently localized in space, then most of these commutators here are almost zero because the Hx are supported far away. And we will always assume that our Hamiltonians are even, that they satisfy the commutation relations I showed you. Actually, we will assume that our Hamiltonian terms are self-adjoint and number conserving. Okay. So this is just a different way of writing the Heisenberg equations of motion. And such an object that, I mean, this is just a formal sum here that will not converge within the algebra, and it will not converge as a bounded operator, but this is what you usually know as the Hamiltonian in Fock space as an unbounded Hamiltonian, but we will not think about this as an unbounded operator in Fock space, but these kind of objects are usually called in this context interactions, or nowadays some people like to call it zero chains. Okay, our Hamiltonian will be of this form, and I'll show you an example in a second. And actually, we will assume that these local terms are really nicely localized, corresponding to short-range interactions in a way I will define in detail in the next session. Okay, now we come to the state. Yeah. I will tell you about the arbitrariness in a second. I just wanted to be brief here. I will give you all the details in the next hour. So actually, I wanted to be brief here. I'm still taking too much time. So let me this is just a teaser. We will do the details. We will define also these norms, these spaces, and all of this. So this will be Fréchet spaces of interactions, Fréchet spaces of localized elements of the algebra and so on. Okay, so a state on the algebra is, by definition now, a linear functional that is positive, normalized to 1. So an element of the dual space. And as you know, in quantum mechanics, we use it to compute expectation values of observables of these elements of A. And because A is strictly smaller than the set of bounded operators on Fock space, we get a larger class, or in a natural way at least, we get a larger class of states, and in particular states now that can describe such systems with infinitely many particles. So the idea of these quasi-local operators is really that, so we agree to only look locally at our state, not globally everywhere at the same time. But we could look everywhere locally. So skip this and yeah. And now the central modeling assumption is that we assume that we have an Hamiltonian, such a derivation, such a sum of local terms, that has a gapped ground state. Now, what does it mean for such a derivation on the algebra to have a gapped ground state is what I've written here. So it's a condition. So omega will be always state, named for a state, and a state omega is a gapped ground state for the Hamiltonian H, or for this Liouvillean, if this inequality is satisfied. I will not go into this right now. This is not at all obvious still to me why this works, but it's an easy exercise you can do. It's not one line, but it's easy. You have to just do a computation to show that in a finite system, if you just say H is a self-adjoint matrix and rho a density matrix, then this condition looks like this. So instead of omega, we have trace rho function operator. And now you can check that this condition here is equivalent if rho satisfies this condition. G is, by the way, a number, which we call the size of the gap, is equivalent to rho being the rank 1 ground state projection of this matrix, and the next eigenvalue is at least G above 0. So this condition in the finite, you can also do this for bounded operators on infinite dimensional Hilbert spaces, but as an exercise, this would be the easiest to see how they are connected. This condition really captures the idea that you have a unique gapped ground state with get G. Okay. And this condition actually does not guarantee uniqueness in general. It would uniqueness of states, of ground states in these infinite volume systems is an extremely hard problem, but it guarantees local uniqueness, and I will explain you next time what that means, not today. Okay, what is an example now for such a system which we want to describe? So let's start, I showed you the Hofstadter butterfly, let's start with a non-interacting Hofstadter model. No interactions, independent fermions on a lattice that Z2 with a constant magnetic field. So actually now the Hamiltonian is just the second quantization of the corresponding one-body operator. And but we always put in for the many-body operator, we always put the chemical potential here to fix, so to say, the density of the system. So we have the one-body operator, the Hamiltonian of the Hofstadter model, minus chemical potential times the identity. And if you look at this, what this is, this just has this form. So we have here hopping from Y to X with the coefficient HB, which contains these so-called magnetic phases So the little b should be a capital B. Sorry for the typo here as well. And so we have in the real Hochstadter Hamiltonian nearest neighbor hoppings, this is a quadratic Hamiltonian, non-interacting Hamiltonian. And it's not so difficult to prove that if mu lies in a gap of the one-body spectrum in this butterfly, then the corresponding many-body operator has a gap ground state exactly in this sense. Okay. H0 is the in the Hochstadter model, it would be just the kernel of the discrete Laplacian without the magnetic field. I just put this here to show you how the magnetic field enters if we nearest neighbor hopping. Exactly. This would be with D0, this would be the discrete Laplacian. And the Hochstadter model gets attaches these phases to the hopping. Okay. No, in this sense here, this term is different from 0, only if x and y are nearest neighbors in that model. But we could allow here also for larger hopping, but in the end, in a certain technical sense, it has to be short range, and I will explain. Okay, and now we now have at least one physically somewhat relevant model where we know that we can have this condition, a spectral gap, and actually it has been shown, and this is a very difficult problem I will not talk about, that for example for this model, the gap is stable if we add small interactions. So I will tell you what this is. I mean, if we add small short-range interactions between the particles, then the gap here will be stable. Then this will be, so for lambda sufficiently small, also the what we call the weakly interacting Hochstadter model will have a gap ground state. There's a proof by Matthew Hastings and a proof by Duress and Steinhofer. They prove stability of the spectral gap for perturbations of non-interacting fermion models on the lattice. You proved this before. I mean, I was about to say this is something which could be proved, and this is very difficult by the techniques of Vieri. And I think people don't cite this work because, and me included at that time, we never understood that you didn't save the stability of the gap, but it follows by, I mean, so to say, this proof here, the Steinhofer has several steps, and the simple step is, so to say, not explicitly given in the paper, so nobody realized, I think. And I have to admit that when Marcello was in Tübingen, the colleague, I asked him about that, and he said, yeah, you're right, it's not proven there. It's, yeah. In a sense, yeah, but it can be proved by, or it is implicitly contained in papers I will mention later on of Vieri et al. But yeah, okay. So this was supposed to be an introduction anyway. I mean, actually, I should also mention that on everything that comes now, I will give history and the literature later on if I do the details. So let me not stick around too long with this. Okay, so what I'm saying here is, again, this is the colored, but okay, I don't know why I had this 1/3 in here, sorry. This is the colored butterfly for the non-interacting Hochstadter model. These colors here are regions where the many-body gap is stable. So where we have, if we are in this parameter range with V and mu, we have a stable, we have a many-body gap. And actually, what I just showed you is if we add here third direction, perturbations with weak interactions, it will still be stable. So we have this I explained before, and I will come back to this, but not now. I mean, the colors are the whole conductances, or mathematically the Chern number in this model, but we will come back to this. Okay, since I have no time for the rest anyway, I can also say one more word here. So what we would like to prove now is the modeling assumption will be that we have a gap. And what we want to what we see here is that the gap regions are open regions. So if we have small variations of V or the chemical potential, that doesn't matter. If we add small interactions, that doesn't matter. We have this kind of stability. So what we want to like to show is that within such a gap region, also called a gap phase, we have Ohm's law with a certain Hall conductance that is exactly constant over these gap phases. So that is what we want to show, that within such a gap phase, we see the behavior we see in the experiment. Okay, good. Now, I'm too slow. Let me finish this with a list of mathematical problems one can now ask in this context and tell you what kind of problems we will be looking at. So first of all, one can ask, for which kind of models can I prove the existence of a gapped ground state? In general, a very difficult problem, and not too much is known. So I gave you an example, weak perturbations of non-interacting systems, and that's basically the only example we have in this context. But we will just assume the gap, and whenever somebody can prove that a system has a gap, we can apply our result. Sorry, say it again. Okay. Then another question is uniqueness, also a very difficult question. Not much is known in general. For specific models, you can do something. So we will not assume uniqueness. We will only assume this local uniqueness, more on this later. Then you can ask about stability under small perturbations, what we just saw. And the only thing is known for fermionic systems is that non-interacting systems are gaps, and non-interacting systems are stable to small perturbations. Okay, and what we want to look at is this class of questions. Now, if we assume that we have a gap ground state in this infinite system, how does such a system respond to external driving, to applying a Hall current or a Hall voltage? And we could, for example, try to show that the response is really linear, that we have an Ohm's law. We can want to show under which conditions can we prove that the Hall conductance is really quantized. We'll also talk about this. And we also would like to understand, this is maybe not so clear at the moment, but will become clear. We will express all these things as expectations of observables. So there will be quantum fluctuations in general, but we don't see them in the experiments. The experiments are basically macroscopic, so we don't see any fluctuations. We always get exactly the same value. We don't get any quantum statistics. And this we also would like to explain, and this is also non-trivial, as you will see. Okay, and my last slide for today, I think it's the last, there's not much more space, is what about classification of these gap phases? This is something I will maybe talk about in the last lecture when I have time. How do we characterize these? What are good definitions in general of gap phases? In the colored Hofstadter model, the definition is obvious, just the constant colors. But how do we capture this idea in general? And can we characterize such gap phases by appropriate heuristic data? Okay, and this was it. And now I thank you very much for your attention. And the second part of the introduction will be given tomorrow. Are there questions for Stefan? I mean, the spec, okay, this is now my interpretation, but I read a lot about this, and actually people like Gerhard also explicitly write this, and I now believe it. My interpretation is that that the idea that the localization is so relevant comes from the fact that people say you can understand the integer quantum Hall effect within non-interacting systems. So it's the interaction is not relevant. I think you have heard this probably also many times. You don't need interaction to explain the quantization. And if you really try to understand now the appearance of plateaus in a non-interacting model, you cannot see it, because if you vary the magnetic field at constant density, once you are at a level where you have an integer filling of some Landau levels, now let's see, you decrease the B field, then the density within the Landau level shrinks, so you have excess electrons immediately hopping to the next one. So you will never be able to vary your mu within such gaps. So you will always hop from one filling. I mean, you will never be able to see a variation in B, wherefore, let's go back here. So if you vary B in this picture, you will never see the plateau, because you immediately hop from this point to this point. Here, but I'm sorry, I have to get used to this controller. Here the idea is really if you, let's say you are here and decrease the D field, then the number of electrons that fit into the filled Landau level decreases, and the electrons have to go somewhere. If they go to the next Landau level, quantization is gone. So they go to the Anderson localized state. That was the picture. But as physicists know since the early 90s, this is not the right picture if you want to really explain where in the whole bars the current flow, and you need to take into account screening and the formation of the local in space region where you have integer filling. And now, if you can easily imagine, if you change the B field here and put the same number of electrons, the location, the width of the strips will change a little bit, but the whole picture remains stable. No, this question I did not understand. I mean, no, I mean, in this non-interacting model, you always have only extended state. In the Hofstadter model. Yes. No, but this is so to say the okay, I mean, this mapping is non-trivial, and I have to say I'm not sure how these two concepts translate, but it's certainly the case that, okay, I mean, yeah, of course, let's say, I mean, this is more about what happens if you go from rational to irrational field. What happens about the spectrum of the type of spectrum? It's right. I mean, in the case of irrational fields here, which you cannot see in this picture, you will have no absolutely continuous spectrum anymore. So, but this is a transition that happens here between rational and irrational values. And as I try to explain, this is completely irrelevant for the physics we're interested in, because we cannot control this. It's anyway very hard to produce some more or less constant D field. So whether it's irrational or rational doesn't matter. But what one can prove, and you know this probably better than I, is that if you just assume, what you cannot do in the experiment, that if you vary here, if you stay there with the chemical potential, it doesn't matter what is down there. If you're in this phase, it doesn't really matter what the spectrum below looks like. You will always have the same Hall conductance. It's stable. So yeah, in this sense, it doesn't see this kind of thing. Mhm. I mean, it's a good question. If M is a finite set, then these are just the bounded operators on that finite part of, then this generates everything. By generate, I mean in the sense of a C-star algebra, so you take finite linear combinations and products, and then the closure under the norm, under the operator norm, and that will not be everything. So, under the norm. So think of it the following way. For people never thought, one sentence, think of continuous compactly supported functions on the real line, and the closure under the soup norm, you get functions decaying at infinity. You don't get all continuous functions. They always have to decay at infinity because of the soup norm, that's exactly the same. So the operators are not really compactly supported, but in a sense, we will make precise next time they decay at infinity. That's how it's done in spin systems. Here I can just say, since this everything are subalgebras of a given algebra founded operators, here just say it's the algebra generated by all creation annihilation operators. But I could also say, take the closure of a block with respect to the signal. Now that the completion is in this, when I do it for spin systems, I take the completion. Yeah, that I try to keep it as simple as possible. Okay, we can discuss about this. I think it's a good idea to keep in mind that these operators we will be looking at could also be understood as just the type of Hamiltonians you have in Fock space as unbounded Hamiltonians. That there's not really happening something extremely different. Okay. Okay. Forget we need in the finance. I want But it's just what you I have to look at it again. It's what people call half of one, right? The one on the one on the line, right? Yes, exactly. Okay, I agree. The mapping is not difficult for me. It's difficult to move with the intuition. About this model, I have a very clear intuition. About the other one.